Right, we're live, I think. I'm going to welcome all those that are here at the BIS in Vauxhall in London. And thank you for coming. And also thank you for risking the trains. I think some of you got through all right. And also welcome to all those of you that are online now from wherever you are in the world. And I hope you can stay with us for this evening's excellent talk. So we're going to really be talking about sort of the history of radar, which is the subject for tonight. It's from ground to space on radar. And what I'd like to do, first of all, is introduce myself, first of all, because I'm Alistair Scott. I'm currently president of the Society and am also chair of the events committee. So if you don't know me, then come to me and we'll ask you what you can do for us, because I'm always looking for new ideas for events and for talks. Finally, if you've never visited us in Vauxhall before, please come and see us, because this place is a bit of a treasure trove in terms of space history. There's an awful lot hidden away in here. We have a comprehensive space library, an amazing collection of 1930s to 50s original artworks and archives that go right back to the start of the space age. So come and see us anytime. Give us a call first and check we're here. Those joining us on Zoom tonight, please use the chat box for your networking and for your questions. It's much easier for us to identify the questions if you put the word question in front or the letter Q, and then we can actually read them out here and get answers from our speaker. So tonight we are extremely fortunate in having with us as our speaker Renato Crocci, who until 2023, in other words last year, was radar chief engineer or chief radar engineer in Thales Alenia Space. Now that is just the Italian branch, or is it?
Actually, the role was
it's worldwide. Oh, right. Okay, it's the top boss. Nice to know. Renato actually graduated in electronics in 1978, and after military service joined Contraves Italiana in Rome in 1980, working on the design of RF analog equipments for radar applications and systems integration. In 1992, he joined Alenia Spazio in Rome, which is now Thales Alenia Space Italia, where he was responsible for the RF and electrical design of the radar altimeter for the Envisat satellite and on several other space projects. Quite a range of experience. He was instrument architect for the Sharad radar sounder for the Mars Reconnaissance Orbiter, which is, I think, still doing its duty up over Mars, and payload manager for the Sentinel-1A radar satellite. As his last assignment in the engineering department, he took technical responsibility for the RIME radar sounder for the JUICE mission to Jupiter. He continued in this role until 2018, when he took charge as radar chief engineer within the chief technical office. He retired in 2023. Thank you very much, Renato. I'll hand over to you. Thank you.
Thank you, everybody. Thank you, Alistair. Let me say that for me it's a great honor to be here, to have been invited to give this speech. This presentation we talk about the history of the radar, which is an incredible history, started 120 years ago, and how it started on ground, then moved to air, and all the application this equipment have in space. There are a lot of radars in space which are used for a lot of interesting things. Radar stands for radio detection and ranging. The definition of radar is that radar is a device which extracts information from the surrounding environment by transmitting electromagnetic waves in the radio spectrum and analyzing the echoes. You can do a lot of things with this information, and there are different ways of processing them according to what you want to get. Starting with the history. Unfortunately, radar was not invented in Britain. The first things which can be called radar was invented in 1994, was patented by Christian Meyer, an engineer from Düsseldorf, who patented this telemobiscope, which was a device which was aimed at prevent collision between ships. So it's very rough, considering the technology of the time. So it has a generator, which was a spark generator, a RF antenna. It was possible to orient the receiver, and it rang a sound when it detected something. And from the test, it has been proven to be able to detect a ship a few hundred meters of distance. There is a legend that he started to work on this device when he witnessed an accident in a harbor due to the heavy fog. Two ships collided with several people dead, and she witnessed a mother crying for the loss of his son, which was embarked upon this. So he decided to work on this type of device. About 30 years ago, that device, which was put in a museum, was taken out of the museum and tested again, and it worked. So, unfortunately, no one was interested in the device from Inspire. So all the activity about radar died for a while until the 30s, because there was two important factors. One, the technology in the radio field has developed a lot. And on the other side, there was the need coming, because the war was approaching. So there was a lot of studies, of course, for military use in many countries. We are talking about Germany and Britain and the US, but also in France, in Italy, in Japan, in Soviet Union, they were working on radars. In many cases, first prototype using continuous wave radars, which use a different transmitter, separate transmitter and receiver, but it was practically impossible to detect accurately the range of the target, and you needed two separate antennas. While with pulsed radar, it's much easier to transmit a pulse, switch the antenna to the receiver, and listen to the echo. So now 90% of the radars work in pulsed way. So the country which was most advanced at the beginning of the war was Germany. In the late 30s, they developed, they were very well advanced in developing radio tubes capable to work at high frequency, hundreds of megahertz. So they have two important type of radar which were operative at the beginning of the war and used throughout the war. Was the Freya, the one you can see on the right, was a search radar operating at 200 megahertz, and the Würzburg, which was a tracking radar. So the parabolic antenna was pointed to the target which was detected by the Freya, and continuously track to provide the continuous information in 3D. On the British side, the British started, let's say, well behind from that. The start was the so-called Daventry experiment made by Watson-Watt, which demonstrated the possibility to use electromagnetic wave to detect airplane. Basically, they had used a broadcast transmitter, put a modified receiver with the cathode ray tube at some miles of distance, and have an airplane flying between them. At a certain point, when the airplane overflow the area, they saw a spike on the cathode ray tube. So in this way, they demonstrate, yes, it's possible to see airplane. The British were well behind the German in technology for high frequency. So for that reason, the famous chain home system, which protected the Great Britain during the war, used the 30 megahertz, which is not a good frequency to make radar, definitely, because the higher the frequency, the better directivity you can get with the antenna given the same size. So 30 megahertz, you need large antenna and have very bad directivity. So, but the problem is that they, in the Britain, they were rushing and they had to use what they have. So the first radar transmitter were derived actually from broadcast transmitters. Nevertheless, even being so rough, they helped Britain win the Battle of Britain. They gave a very important contribution. In the US, they started earlier. In 1934, they have already started officially the activity on the radar. At the beginning of the war, they already had radars installed several units. Several ships also used on ground. One point important about the American contribution was the microwave magnetron. The microwave magnetron was a device which was invented in Britain, but the most important development was done in the United States. So the Tixer mission was Dr. Tixer was responsible, the scientific responsible for the British defense. He went before the US entering the war, went to the States to exchange technical and scientific information about weapons. So among these, the British disclosed the work they have done on the microwave magnetron. The point is that the Americans were able to mobilize an important scientific force, just as quantity. They put their best scientists working on radars. In fact, most of the radar theory was developed in the States in that period. Coming back to the microwave magnetron, we have just said that the frequency is important. So going up in frequency with significant power is important to have compact radar with reasonable size and antenna. And the microwave magnetron can generate high-power pulses of several gigahertz, not megahertz, gigahertz of frequency with a relatively compact device. So this gives the Allied, so British and American, a great advantage over the Germans because they could go up in frequency, have very compact radar, high resolution, and so from that on, they took the edge of the radar development. Okay. After the magnetron was an oscillator, so every time it was started, it generated pulse with a random phase, which is a problem for several applications when you need to keep a coherency between one pulse to the other. Some other tubes were also developed. For example, the klystron, which instead is an amplifier, so you can keep a reference oscillator, amplify the pulse from this, and keep a memory of the started phase. And later, also the traveling wave tubes, which is also an amplifier, but have the great advantage to operate with on a very large bandwidth. So which is important for several applications. Now, actually, the use of TWTs is decreasing because now we are going for most application on solid state, thanks to the advance in technology development.